Hi everyone, today it's probably the last video about the Sabianca's 1989, as you remember, theorem. After this video we're gonna move on to something more specific and something, from my perspective, more interesting and more practical, because this paper is the foundation for deep learning, as I think. And we're gonna move to something like CNNs, something about that, or something about different stuff. But today we're gonna find out about the results for other activation functions. And to be true with you, from my perspective, this naming for the paragraph is not really cool, because what we're looking for is that, going back to our graph, we've discussed this space, this cube, and the important thing here is that this cube basically involves continuous functions. So, like, to better illustrate that, we have something like let's firstly represent them in 2D, because it's it's easier for me. This cube is actually talking mainly about smooth curves like that, maybe this one. So, like, smooth continuous curves without any glitches, any holes in them. So yeah, but essentially what our space does and what's extremely important are decision functions and other types of functions. So, for example, this is a function, we want to prove that. So this is a function, we want to prove this one. Maybe something that just gives numbers in some whatever order, or some function that has a hole in it, like that. So we want to represent them. So we're gonna be proving that, essentially following the same direction. So yeah, what is that? In this section we discuss other classes of activation functions that have approximation properties similar to the ones enjoyed by continuous sigmoidals. Since these other examples are somewhat less practical interest, we only sketch their corresponding proofs. So yeah, they have less practical interest, but basically they don't, I think. But whatever, we don't have extended proofs for them. There is considerable interest in discontinuous sigmoidal functions, such as hard limiters. So yeah, we're looking for limiters. Discontinuous sigmoidal functions that are not used as continuous ones, because they lack of good training algorithms, but they are theoretical interest because they close relationship to classical perceptrons and common networks. So again, we're just talking about those things. Assume that sigma is bound to measurable sigmoidal function. We have an analog of theorem 2 that goes as follows. Let sigma be bounded measurable sigmoidal function, then finite sums of other one-layered neural network are dense. In other words, given any f belongs to this thing and error, there is a sum of j of x before and which. So we are essentially proving that to all of the functions, discontinuous, broken ones, and so on. But basically what I think is that we actually don't care, because what I think is that we can basically represent the function that we were talking about, like, yeah, I'm sorry, I mean, it goes like that, it goes as follows, like it's this one. But what we can actually do is that we can create a similar function that is continuous, I think, and we wouldn't be really bothered with that. So yeah, like that. So those are literally the same, and I think we don't really care about them, because, for example, if we have function like close relationship that it's bad. That gets like 1 or 0, like 1s, 0s, whatever. We wouldn't actually care if we have something like that, because like this is a 0.5 point, and if we are above that, so we're gonna go to this thing, and we are below that, we're gonna go to this thing, and if we are more than that, we're gonna go to this thing accordingly. So I think you get that. The proof follows the proof of theorems 1 and 2 with obvious changes, such as replacing continuous function by intangible functions and using the fact that it's dual, whatever this means, I think. The notion of being discriminatory accordingly changes to the following in the condition that, so we have some kind of a function that zeros this whole thing. For all implies that, so yeah, the property of the discriminatory function, again, it's restated. General sigmoidal functions are discriminatory in the sense as already seen in lemma 1, because measures of the form hx dx belong to M. Yeah, general sigmoidal functions, we have already seen them, and we have even proved them. We have even proved that. So since convergence in L1 implies convergence in measure A, we have an analog of theorem 3 that goes as follows. So we're looking for an analog. Whatever, so there is our neural net, and for any function we can represent it partition decision. So we're looking for the same theorem, but just with decision functions, just like fx is more than 1, we'll get 0, something like that. So again, we're stating that a number of other possible activation functions to be shown to have approximation properties similar to the theorem 1. Okay, we get that those include sine and cosine functions, linear combinations. So yeah, that's just talking about the, as I remember, the like, hell, I forgot his name. The Fourier transformation guy who has actually proven that trigonometric polynomials, which are classically known to be complete. Interestingly, the completeness of trigonometry was implicitly used in lemma and Fourier transforms. Yeah. One mapping property. Another classical example is that exponential functions, and the proof that again follows from direct application from. Yeah, we basically proved it for explanations either when we were using like Fourier transformation. Exponential activation functions were studied in Palm P, where their completeness was shown. A whole other class of possible activation functions have completeness properties in this thing as a result of the okay, for example, suppose that function non-zero integral. Okay, so I think what we're basically doing here is that we are saying again that so we are doing, I think, the same thing for actually decision function. So we are saying that this is what we want to prove, that h is 0. If this is true, we have this thing that actually linear functional that is used for our h to make it 0. Alright, so this implies if the function is discriminatory that linear functional is 0. Yeah. But if the linear functional is 0, so we can use an exponent, and this exponent it's always non-zero, alright? And if the exponent is non-zero, so h is 0. So yeah, there is a contradiction, so that's it. Yeah. The use of theorem leads to some other course activation functions that have the completeness. Consider the following activation function of variables. Yeah, but basically going a bit farther from this paper, because I don't want to dive extremely in depth, because like it's not extremely complicated, but he's just proving that activation functions can approximate decision functions. But what I wanted to mention for you is that obviously we are not gonna we're gonna use this theorem, but what we want to do is that we want to understand it like with the back of our mind we want to understand it in the level of feelings, but not just as math concrete things that we don't actually understand. So what we're saying is that we can approximate decision function, but again, let's let's find this Desmos Online thing, and I will explicitly show you what I meant. Whoa. Yeah, like that. Oh, hell. But whatever, it works, so we don't care. So yeah, what I say to you is that, let's say we have some property like y equals 1, x equals 3. No, we want to find like y is always 0, so x like 1, 0, 1, 1, 1, 2. Yeah, I'm sorry. What I mean is by it's a bit more complicated. Let's do like that. 10, 1, like say 9, 1. Let's say like 8, 1. So we have and here we're gonna do like 0, negative, like negative 1, negative 1. Yeah, let's do like that. Negative 2, 0, negative 5, 0. So we have this sort of function that is actually a decision function. So if x is 8, then y is 0. And we can basically approximate it by our sigmoid again. So it actually represents that our sigmoid basically works. Of course it has some mistakes, but still, again, it just works. So yeah, we can approximate them. So we're gonna get the same values where the same values are, and we don't actually care. So if there is no value, we cannot actually see that if our function gives here a value and the initial function doesn't. So why would we actually be bothered about that? So that's all. And to mention other ReLU functions, as sigmoid is not really convenient. A lot of people just use ReLU function. So what ReLU function is? Let's say we have like maximum from 0 and x. So this is the ReLU function. So because the only property that we care about is that our function should be not linear. It should be able to cut the space into two parts. And ReLU is just, I think from our perspective, it's the best function ever. I mean, non-linear for neural nets, because maybe better if we show it like that, because it explicitly gives us an opportunity to take the easiest function possible, so y equals x, and if x is below 0, so it just spits like y to 0. So that's it. And we can of course take activation functions for neural nets, like ReLU, sigmoid, what other ones exist. So ReLU variance, leaky ReLU let's look for something mesh error functional. Activation, I mean. So yeah, it's something like that. It's just like ReLU, but it's mesh. So you get what I'm saying. And so this basically provides us with an algorithm that can replicate any existing function, and that's extremely important because everything that we would be using up to like transformers, like ChatGPT, generative models, whatever, audio recognition, we're gonna use neural nets. And I think we're gonna be building neural nets. So yeah, that's it. That's, I think, all. So this paper is ended up. I don't want to go through summary because it just restates all the things that we were talking about before. So that's it. Thank you for listening. Bye. I'm going to return with the next paper.